In May 1859, Isambard Kingdom Brunel was carried across his own bridge on a flatbed railway wagon. He was too ill to stand. He lay on the wagon and looked up at the wrought iron tubes and chains above him. The structure he had spent 7 years designing and 4 years building across the River Tamar between Devon and Cornwall. He had not seen it finished. He saw it now, from below, on the day of the opening inspection. 4 months later, he was dead. The Royal Albert Bridge at Saltash has carried every train crossing the Tamar between Plymouth and Cornwall ever since. 165 years. The wrought iron that Brunel specified, the tubes, the chains, the suspension rods, is still in place. The 2 main spans he calculated, still standing. A man who never saw his bridge completed, built something that has not required fundamental reconstruction in a century and a half. By making a small gesture and clicking the subscribe button beneath this video, you perform a small action with great significance to us. By pressing it, you understand that the matter is not about the magnitude of the act, but its meaning. It shows that the effort, the late nights, and the discipline required to bring this forward mattered to someone on the other side of the screen. Like the video, subscribe to the channel, even leave a comment below suggesting which structure you would like us to cover next. The crossing of the River Tamar at Saltash was a problem that the Cornwall Railway had carried unresolved for a decade before Brunel was formally appointed to solve it. The railway had reached Plymouth from London by 1849. Getting it across the Tamar into Cornwall required bridging a river that was not merely wide, 345 feet at the crossing point, but deep, tidal and busy with naval and commercial traffic that the Admiralty insisted must not be obstructed. The Admiralty's requirement was clear: 100 feet of clear headroom above high water across the full navigable channel. That dictated everything that followed. 100 feet of clearance above a tidal river, 345 feet wide, carrying the weight of a fully loaded broad-gauge train, anchored to ground conditions that Brunel would spend years investigating before he was confident enough to commit to a design. The geology beneath the Tamar at Saltash was Brunel's first problem. The riverbed in the center of the channel was not the solid rock that a pier foundation of this size ideally required. It was an unpredictable mixture, rock in places, compressed river sediment in others, with no certainty at any given point about what lay beneath. Brunel commissioned a series of borings to map the riverbed. What they returned was not reassuring. The only viable location for a central pier, the single pier that would divide the span into 2 crossings of manageable length, was over ground that offered adequate rock at a depth of 80 feet below the surface, 80 feet below a tidal river, in compressed silt overlying fractured slate. The pier would have to be built from the riverbed up through 80 feet of difficult ground before it reached the level where it could begin to support the structure above it. Brunel's solution to the central pier was a wrought iron cylinder, 70 feet in diameter, sealed at the top and pressurized from below to allow workers to excavate inside it, while the water pressure was held back. This was compressed air working, pneumatic caisson construction at a scale that had not been attempted in Britain at the time. The cylinder was floated into position on the Tamar in 1853, positioned with considerable difficulty against the tidal current over the central pier location, and sunk by controlled flooding of the outer chambers. Men worked inside it in pressurized air, removing the riverbed material by hand and by shovel, guided by Brunel's borings but frequently encountering conditions the borings had not predicted. The pressure required to exclude the water at 80 feet depth produced physiological effects in the workers that were not yet understood. Joint pain, neurological symptoms, collapse on returning to surface pressure. The condition would later be named caisson disease. At the time it was described in the site records simply as illness. As the excavation deepened and the cylinder settled, the masonry and concrete that would form the pier base were packed beneath and around it from within. When rock was finally reached, the foundation was complete. The cylinder then became the permanent outer shell of the pier shaft rising above it. The central pier of the Royal Albert Bridge was built from the inside of a pressurized iron tube, 80 feet below the Tamar's surface, by men working in conditions that no regulatory framework then existed to define or constrain. The span design that Brunel developed for the Royal Albert Bridge combined 2 structural principles that had not previously been used together at this scale. Each of the 2 main spans, 455 feet from the central pier to the shore towers on each bank, consisted of an oval wrought iron tube curving upward in a parabolic arch, from which suspension chains hung below, connecting the tube to the deck. The tube pushed outward at its supports. The chains pulled inward. The two forces balanced each other across the full span length, meaning that the horizontal loads transmitted to the shore towers and to the central pier were dramatically reduced compared with either a conventional suspension bridge or a conventional arch bridge acting alone. The piers did not need to resist the full outward thrust of the arch because the chains absorbed it internally within the span. They carried vertical load almost exclusively. For a structure founded on the ground conditions Brunel was working with, a central pier on fractured slate reached only at 80 feet, and shore towers on riverbank ground of variable quality. This was not an aesthetic preference. It was the only structural logic that made the crossing buildable on this site at this height above the water. The wrought iron for the tubes and chains was manufactured to Brunel's specification in Birmingham and transported to the Tamar by rail and barge. The tubes were assembled on the Devon bank in sections and floated out into the river on pontoons in a sequence that required precise coordination, tidal timing, river traffic, and the positioning of the pontoon fleet. The first span was raised in September 8. The tube was floated into position, the pontoons were pumped to lower them in the water, and the tube settled onto the pier and shore tower supports. The operation was watched by a crowd estimated at several thousand people gathered on both banks. It worked on the first attempt. The second span was raised in July 1858, using the same method. Brunel was present for both raisings, though by the second, he was already in declining health. The Cornwall Railway's broad gauge line opened across the Royal Albert Bridge on 4 May 1859, with the inspection run that Brunel observed from his flat wagon. Prince Albert had already given his name to the structure, a recognition from the royal household that was sufficiently unusual for a piece of railway infrastructure to indicate how seriously the bridge and its engineering were taken even before the opening. The public ceremony that followed drew crowds to both banks of the Tamar. The bridge that had taken 11 years from commission to completion, 7 of design and study, 4 of construction, was open. Brunel died on 15 September 1859, 4 months after crossing it, lying on his back on a flat wagon. He was 53 years old. The line converted from broad to standard gauge in 1892, which required changes to the track and to the deck structure, not to the wrought iron tubes and chains above. Brunel's main structural elements were not touched by the gauge conversion. They were simply not what needed changing. The decision Brunel made at every stage of the Royal Albert Bridge's design was to use more material than the minimum load analysis required. The wrought iron tubes are thicker walled than the 1854 calculations strictly demanded. The chains carry a factor of safety that the traffic volumes of 1859 could not justify, and that the traffic of 2024 has not yet exceeded. The shore towers, built from cast iron columns and masonry, were proportioned for loads that contemporary broad-gauge locomotives could not produce, and that took the development of the 20th century's heaviest freight locomotives to begin to approach. A bridge specified to the minimum required for 1859 traffic would have been a different structure entirely. Lighter, narrower in its safety margins, requiring upgrading or replacement as locomotive weights doubled and then trebled across the century that followed. The Royal Albert Bridge required neither. The name Brunel has been fixed to the portals of the bridge since 1859, placed there after his death as a permanent attribution. It is the only bridge in Britain that carries the name of its engineer on its structure as a built-in feature rather than a later addition. Every train that crosses the Tamar passes under his name, in both directions, twice, 165 years of trains. The wrought iron he specified is still there. The chains are still in tension. The tubes are still in compression. The central pier, founded on fractured slate 80 feet below the Tamar, has not moved. Network Rail has assessed the bridge on a regular inspection cycle since it assumed responsibility for the national railway infrastructure. The assessments have consistently found the main structural elements within safe load margins. Some maintenance has been carried out on the deck and on secondary structural elements. The wrought iron tubes and suspension chains, the elements that Brunel designed and that have been continuously loaded since 1859, have not been replaced. They are monitored. They are painted. They carry the trains. A structure of this ambition designed today would face a procurement process that would almost certainly produce a different answer. A cable-stayed bridge, or a modern suspension design optimized for construction efficiency and for the defined service life of 100 years, with a major maintenance interval at 50. Cheaper to build. Specified to last long enough to justify the capital cost. Designed for the traffic anticipated over that service period, with an assumption that future requirements beyond it would be someone else's problem. Brunel designed for the Tamar crossing as a permanent problem, requiring a permanent answer. He built the answer in wrought iron in 1859. It is still answering. Here again you see a mega structure born from the intelligence of a talented engineer. If you would like more videos like this, please like the video and subscribe to the channel.